So now we're going to talk about beam deflection, and beam deflection is kind of like the extension of the shear moment diagrams. So if you remember way back when we were talking about like the bending and transverse stress, we did a little mini introduction to the shear moment diagrams, and these are actually from statics, I think is usually where you first see them. So the idea is if I have a beam, it's got some loading on it right here, I got a pin, and I got a roller, and those create forces, right? This has a force in any direction because it stops rotation, or sorry, it stops translation but not rotation, and then this roller only stops translation vertically. I've got some applied loadings. I've got an applied couple moment, which I don't know if we've gone over like how this technically works, but basically the idea is that if you apply like a force one way and then a force the other way at some distance, this creates a moment, right? But whatever point you pick, the only distances that matter are the perpendicular distance, so this distance here and this distance right here, right? So basically, if these are the same force because they're equal and opposite, then just this entire length right here times the force is the same as half this length times the force plus half this length times the force, right? And no matter where I move it in this direction, anywhere along this axis, it's not going to change because it's only the perpendicular component. And when I move it along this axis in this direction, the amount that this part's length increases is exactly equal and opposite to the amount that this length decreases, which means that the moment is the same. So when we apply a couple moment, we're basically literally just adding a moment to our thing. And then last we have the distributed load. So all of these are going to change the internal shear force that one segment exerts on the other. So if we go ahead and we look right here, based on our sign convention, where like on the left we have upward shear and on the right we have downward shear, and then the bending like this. So this is my shear convention, and this right here is my moment convention. Based on those conventions, we can kind of plot the internal shear. So right, this AY is going to have a vertical force that's going to increase the internal shear. Then we just have the same shear, constant, 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 until we have this applied load. That brings that down, and then it's constant again until we have this distributed load, which is going to make it move linearly down because we get more and more force, shear force, as we go across this beam. And then this applied load right here is going to bring it down again. And then it should always be 0 on both ends because this entire thing is in equilibrium, right? All of these forces in the y direction should sum up to be 0 because the part's in equilibrium. And then we can also have the internal moment diagram, which, based on our derivations here, where we kind of just assume that we took a slice, it's going to have some shear on the left, some moment on the left, and some shear and moment on the right over some distributed load. All of this equals out so that the change in shear is basically the same as integrating our applied distributed load across the beam, and then the moment is just the integral of our shear force, where this doesn't take into account our jump discontinuities. So whenever you have an applied moment or an applied force, that's just going to create a jump which isn't handled by the integral. So like right here, you could see that we have right here we kind of have a jump in the moment. I don't know what happened. I guess the diagram got a little bit cluttered. So beam deflection, we're basically going to upgrade these shear moment diagrams. So you see right here, I've got a pretty simple setup. I just have this beam right here, and instead of a distributed load, there's just one force right in the middle. So my shear is going to go up by P/2 on the left end right here. It's going to stay constant, constant, constant until that shear force brings it down to negative P/2, constant all the way across to the end. When it goes back to 0, both sides start and end at 0, so we're looking pretty good. When we take the integral of this, we're going to get the moment. So the integral of a constant function is linear, so we get linear increasing, increasing, up to this maximum bending moment right in the middle right here, and then it's going to decrease all the way back to 0 because, again, the sum of the moments has to be 0 because this thing is not angularly accelerating. Now what we're going to do, though, is we're going to add in two new ones. This one right here, theta, is basically the slope of our beam, but then the really interesting one is this v right here, which is our deflection. And this deflection diagram is literally basically a graph of the shape of this beam under the applied loading. And the reason we couldn't do this with statics is because we didn't have material properties, right? You can imagine if this beam is made out of like steel, it's going to bend a lot less than if it was made out of like rubber or something. So there's going to be an E that shows up in these equations once we start getting into them. So there are two ways we can start deriving the relationship between the deflection and the internal loading. So if we go back to the previous video where we were talking about buckling. So when we're looking at these beams, we went ahead and wrote out the equation for the curvature, and then we said that the slope is small enough because it's generally deflecting very, very little, that this slope term right here we can essentially set to 0, which means that our curvature is just the second derivative of our deflection, or our change in this lateral direction, with respect to x, which has to equal m over EI, and that comes from our derivation with the bending and transverse, once we get down to bending right here, you can see we have our curvature, which is 1 over rho. If we divide across this e, we have the m over ei equals our curvature. So if we go ahead and we solve this, we get that m is equal to ei times the second derivative of our deflection with respect to x. Another way we can get this result is we can kind of imagine like our deflected beam across some loading. So we could say that our center of curvature right here, if we pick some point, is going to have a radius rho. It'll have some differential angle that is tracing across d theta, and it'll have a differential length ds. And then down here, when we break this open, we'll have our ds along this hypotenuse, a dx and a dv, because this is my x-axis right here, and this is my v-axis, and this angle right here is theta. And just to kind of convince you that this theta right here, if you would have a differential of this theta, it would actually be the same as this d theta up here. One way you can think about it is that this d theta is basically related to the curvature, right? So if this is our theta right here, our slope, a d theta is basically a change in slope, which is exactly what happens when we have the curvature here. So basically, the more we trace along this angle at our radius of curvature, the more we're going to get a change in slope, which means that this d theta and these d thetas are the same, and we can set them equal to each other. So anyway, we can go ahead and say that dv dx has to equal, right, our tangent of theta. Then we're going to use the small angle approximation, which is basically the same as when we were back over here at buckling, setting this equal to 0. So this is, we're just going to say this equals theta approximately. But we also know that d theta, based on the definition of radians, is equal to the arc length traced out ds divided by our radius of curvature right here. And we're going to do another approximation where basically if this angle theta is small enough, ds and dx are essentially the same as a differential. So we're going to divide this over, and we're going to say that 1 over rho is equal to d theta over ds, which is basically equal to d theta by dx. So now if I take the derivative of this one right here, what I'll get is that d theta dx equals the second derivative of my deflection with respect to x, and that also equals 1 over rho, which, based on our work with the bending and transverse stress, is equal to m over ei. And this really gives us all of the information that we're going to need, right? So when we look up here, we made this theta diagram, and this is exactly the equation that we're going to use to get our theta diagram. So basically, if we just integrate m over ei, then we can get theta as a function of x. And obviously, we'll need our initial conditions, which will be based on geometry or just things we know about our physical setup. And then, once we have that, we can integrate again, because we've already integrated this whole thing. So this is basically just a single differential. We integrate again to go from theta, which is our angle, to our deflection diagram right here. So let's go ahead and look at an example to maybe make this a little bit clear. So we have our beam right here. It's pinned on one end. We've got a roller on one end, and then we got a distributed load across this. And we want to give the function for the deflection of this beam. So the first thing we need to do, right, if we want to get v, is we're probably going to have to get theta first, because we'll integrate theta, right? Which means that we're going to need m. E and I are both properties of the material, so we don't have to worry about that. But we need m as a function of x. So if we come back here, what we're going to do is we're going to create a section. We're basically going to cut out a little section of this beam, right? We'll call this distance right here x. We'll have our loading, so we'll have our distributed load right here, w. And then we'll also have our reaction force right here. It's a pin, so there could technically be 2, but basically there's no forces in the x direction, so if you sum them, it's just going to be 0, so we'll go ahead and drop it. So this right here is ay, and because of the symmetry of the problem, right, we have a reaction right here, ay and by, and because both of those are actually going to be equal to w times L, which is my entire equivalent force on this beam divided by 2. So I could say ay equals WL over 2. And if you don't see that, you could just do some of the forces, some of the moments about some of the forces in the y direction, and then some of the moments about one of these points, and it will work out to be this. And then we'll also have our internal shear force, V of x, and our internal moment, M of x. So what we're going to do is we're going to sum all the moments about this point. We'll just call this point, like, I don't know, we have A, we have B, so we'll call this C. So if I add up all the moments about C, this has to equal 0 because we're still in equilibrium. This is going to equal M of x minus x times ay minus x times w, which is the equivalent force, times x over 2, which is the point that's acting at, right? Halfway through this section right here, which means that my m as a function of x is equal to x, and then I'm just going to go ahead and put wl over 2, because that's what our ay is, minus, and then we'll have a 1/2 wx squared, okay? So now to get theta of x, all we have to do, coming back here, is integrate m over ei. So we get this is equal to 1 over ei, because these are constants, I'm just going to pull them out. Integral of, let's see, we have a 1/2 wlx minus 1/2 wx squared, and this right here is all dx. So this right here is my m, just to be clear about what's going on here. It actually looks like I dropped a negative sign. So the positive direction is this way, which means that this distributed load is actually going to give us a positive moment right here. So now we go ahead and compute this integral. We'll get this is 1 over ei times, and we'll have negative 1/6 wx cubed minus, and this should be like 1/4 wl squared, and then we'll plus a constant. We'll call it c1 because we're going to end up getting 2. Now we can say that v, which is my deflection, as a function of x is equal to the integral of theta of x dx, which is equal to, right, 1 over ei, integral of all of this. And then we'll have plus c1. And now if I evaluate this integral, what I get is that this is going to equal 1 over ei times. And now to get rid of these constants, we're going to think about initial conditions. So if we go all the way back up to my beam right here, because it's pinned at this end and it has a roller at this end, at both of the ends, the beam can't move up or down, which means that the deflection at both of those points has to be 0. And those are the two initial conditions we're going to use. So we say that our deflection at x equals 0 has to equal 0. And if you think about plugging in x equals 0 into this, I'm going to get a 0 here, 0 here, and 0 here. And if I want this whole equation to equal 0, then that means that my C2 has to be equal to 0. Now the other initial condition is that our deflection at L has to equal 0. So if I go ahead and plug this all in, if I go ahead and plug in L for all of this, now I can solve for C1. So now plugging it all back in, I get an equation. I get an equation for the deflection of this beam. So this is our final equation of the deflection of the beam, and just to give you an idea of what this looks like, I went ahead and plotted it in Desmos real quick. You can see that between 0 and my length, which I have set to 10 right here, there's kind of like this downward bend, which is exactly what we would expect, right? And because we're using a fourth order polynomial to model all this, there's some weird behavior where it needs like 4 zeros beyond the ends of it, but like it doesn't even make sense to talk about what's going on there anyway, right? Like there's no shape of the beam beyond the ends of the beam. So even though it looks a little bit weird, like past here and all of that, there's no like physical meaning for what that is. That's just kind of like a remnant of how the math works out.